Hello everyone, I hope you are doing well. So in today's video, I'll be going through the 2018 physics exam for the Northern Hemisphere multiple choice section. Like always guys, before I start this video, if you guys want private tutoring in specialist methods, physics or chemistry, you can always email me through this email. And yeah guys, let's smash through this video. Question 1. Engineers are measuring the force due to Earth's magnetic field on a supply wire on a railway line. The wire runs east-west, so east is here, goes to west, so from east to west is a wire. Say this is a wire. So this is the wire. Yeah, it's like a wire from east to west and carries a current of 2000 amps. So let's say that's 2000 amps. Easy. Just put that there. Earth's magnetic field is horizontal and due north at the place where measurements are taken. So we have due north and magnetic field, which is B. And yeah, as we can see, they are perpendicular, which means there is a force. And that force, remember, using your right-hand slap rule, you remember your thumb is going to go where the direction of current is, and your fingers are going to go to the direction of where the magnetic field is, which in this case, for this question, the actual force is going to be acting into the page. Beautiful. The engineers measure the force on the 10 meter length of the wire to be 1 Newton. Easy. So we know the force is 1 Newton. And we also know the length of the wire, which is 10 meters. Which of the following best gives the strength of the magnetic field at this point? Beautiful. So you should know we should use the formula. F equals NLLB. Sorry. IB. So of course this is the length, this is the current, and this is the magnetic field, and N is the amount of coil, like how many turns. Well, in this case it's just a single wire, so it actually is just 1. So we draw it as well, the force is 1, N is just 1, L is the length, which is 10, I is the current, which is 2000. Let me just put this down so we can write more. And B is what we're trying to find out. Hence, your B value is just 1 over 10 to 1000. And let me just do that in my calculator and let's see what the answer is. So 10 times, 10 times 2000. That gives me 5.0 times 10 to the power of 1, 2, 3, 4, 5. Negative 5. Teslas, and which looks like B is your answer. Nice and easy. Next question. Question 2. So we're given the mass of Mercury, the radius of Mercury, and the universal gravitational constant. The gravitational field strength at the surface of Mercury is closest to what? What a beautiful, nice, easy question. So, you should know the formula. G is, G equals GMR squared. To calculate the gravitational field strength. So, our G is going to be our universal constant, so 6.67 times 10 to the negative 11. Mass of Mercury, because that's the one that's creating that gravitational field, 3.34 times 10 to the power of 23, all divided by the radius squared, which in this case is just 2.44 times 10 to the power of 6 squared. And it makes sense. Yep, the radius of Mercury, if you're hitting the radius of Mercury, that is the surface as shown here. So if I drew a circle, say the midpoint, and so the radius of the Mercury is actually where it's the distance between the surface and the center of the planet, which is great. So, yep, so let's use that calculator and see what this gives us. 6.67 times 10 to the negative 11, 3.34 times 10 to the power 23, and 2.44 times 10 to the power 6 squared. So, alright, that gives me 3.74, which looks like C is your answer. Done. Have a look at the next question. It says, a Van de Graaff generator, which is a piece of electrical field demonstration equipment, consists of a small sphere that is electrically charged as shown in the diagram. Okay, we can see it's a sphere that is, positively charged. A particular Van de Graaff generator has a sphere that has a charge of 5.0 times 10 to the negative 7 coulombs on it. Take the Coulomb's law constant to be this. Which of the following best gives the magnitude of the electrical field at point X in the diagram above as 0.5 meters from the sphere? What a beautiful, nice, easy question. So we know because this sphere is actually going to be generating an electrical field. And because it's a positive, it's going to be, the arrows are going to be outside. Now, of course, there's going to be like, it's a positive, so it's going to generate an electrical field. The closer it is to where the source of the field is coming, the stronger. So the more you go, the less it becomes strong. So the way you just do this is we want to calculate the electrical field. You should know we use E to calculate electrical field is equal to KQ squared. It's pretty much the same formula like this, but now we're dealing with charges. And so, yeah, let's put what we have. So K is 9.0 times 10 to the power of 9. Q is the charge of the source, which in this case is our 5.0 times 10 to the negative 7, all being divided by r squared, the radius, the centers. And as you can see, it's 0.5 squared. Easy. Let's put that in our calculator. 9.0 times 10 to the power 9, 5.0 times 10 to the negative 7, and 0.5 squared. So that gives me, it gives me 1.8 times 10 to the power of 4 to the power of 4. Which one is that? That looks like C is your answer. Done. Question 4. A simple DC generator consists of two magnets that produce a uniform magnetic field in which a square loop of wire with 100 turn rotates at a constant speed, and a commutator as shown in the diagram. Aha, this is the key here. It's a commutator being used. All right. Which of the form best shows the displays the observed on the oscilloscope? I can't even say that word. So A is absolutely wrong, and here's why. It will be right if they used slip rings. Because they are using what we call a commutator or a split ring commutator, what's going to happen is every half turn, the voltage gets reversed. For example, so this is one full turn. Every half turn which occurs here, this one over here gets reversed. So it will be like this. Hence, what's actually just the graph will actually just will look like this. It'll be pulsating, so these will be gone. So hence, that's what when you have a commutator being used, not a slip ring commutator, this is what you want to see. So A is wrong, or B is rubbish. C is wrong because it's saying the voltage is constant. The voltage will be changing, so that's wrong. And D is beautiful. D actually represents, as you can see, those voltage are pulsating every half turn. Done. Nice and easy. So question 5. So question 5 to 7. Okay. A step-down transformer is used to convert 240 volts RMS AC to 16 volts RMS AC. Assume that the transformer is ideal. What do they mean by ideal? It means that the power on the primary coil is going to be equal to the power on the secondary coil. So there's no power lost, it means. For example, let's just draw a transformer. Like this. That is a transformer, and of course, this part here is the input or the primary section of it, and this is your secondary, which is the output. And in this case, we have 240 volts RMS in here, and so the output would be 16 volts RMS. Done. Which of the following best gives the peak voltage of the input to the transformer? Here is the input, this one. Hence, we just want to calculate the peak voltage, which is Vp. Now, we know to do that is we just multiply it by root 2 times the voltage RMS. So it will be root 2, and we know it's times by 240, and that will be 240 times root 2. That gives me 339, which is C. Done. Question 6. The ratio of turns in the primary input to the turns in the secondary output is given by what? So what we're trying to do is we want to calculate the ratio N1, which is the primary input turns, and N2. So the ratio between them. If you actually don't know, this is actually equal to V1, the ratio between the voltage of the primary to the voltage of the secondary. So what we can do is we just can calculate that, and it will be the same as that. So what is the voltage of the primary? It's just 240 volts. And what's the voltage of the secondary, which is 16? Done. So that is here, simplifying it. So 240 divided by 16, so it'll be 15 to 1 ratio, which looks like A is your answer. Question 7. The power input to the primary of the transformer is 30 watts. So what we're doing is we're actually putting 30 watts here. Now, of course, because it's an ideal transformer, in the output, it will also have 30 watts because it's ideal. There's no power lost. Which of the following best gives the RMS current in the secondary output? So here, what is the secondary output? And that's very easy. So we know that power is equal to voltage times current. So, and we know the power on the secondary output is actually just 30. So we put 30. The voltage is 16 and times by the current. So the current will just be 30 divided by 16, which gives you 1.875, which is approximately B. Done. So this goes for question 8 and 9. A 1 kilogram mass, okay, is attached to a string, is hanging 4 meters from the ground. Okay, assume that the string has no mass. The string is connected to a 4 kilogram mass on the horizontal frictionless table. Every time, be careful with this word, frictionless. It means no friction. Beautiful. As shown below. The masses are released from rest. That is very, very important. Always highlight that, from rest. And the acceleration is 1.96 meters per second is observed. What's going to happen? So, of course, when it's released, this is going to be, this mass over here is actually going to be accelerating downwards. And this here, this mass is actually going to be accelerating to the left. And of course, they're going to be accelerating the same rate. So if this is accelerating at 1.96 meters per second, this also must be accelerating by this much. And also, be careful. This here, this is the direction. So when we're dealing with calculations with the 1 kilo, we're going to take down as positive. And when we're dealing with this mass, we're going to be taking to left positive because that's where our acceleration direction is. So let's have a look at the question. The tension in the string is closest to what? So actually, let's just draw all the forces that we can see. So for the 1 kilogram, we will have what we call the force of gravity, which in this case will be mg. In this case, the mass is 1, so it's just going to be g. And of course, we're going to have a tension in that string. Sorry, it's not the best, but yeah, it's supposed to be on the same. Yeah, there's going to be tension on that string. There will also be tension coming to this string, and these two tensions are going to be the same because they're acting on the same string. We will also have, 4g. So, sorry, mass times, the force of gravity on this, which is mg. But because it has the mass of 4, so it'll be 4g. This is not very important because it really doesn't affect, because we're taking this, it's because it's accelerating to the left. We're only going to use the forces that are right or left. So this, and yeah. For example, if we were doing calculations with this, as you can see, down is, positives. We'll only take the vertical directions to do calculations. Well, in this case, yes, this is vertical and this is vertical, so these are great. But the problem is this is quite useless because tension is great because it is in the same direction as the acceleration, but yeah, this here is not, it's quite useless, so let's rub that out. And yeah, we can actually use either of them to calculate the tension. For example, let's use this here to calculate the tension. We know that F net, which is the net force, is equal to the sum of all forces. Because we're taking down as positive, we're going to, add these two. So this is going to be G minus T. And why did I write that minus? Remember, we are adding them. And because this is the opposite direction, we're going to have put a minus. Beautiful. And what do we know F net to be? It's actually just mass times the acceleration. Because we know, the mass, we're dealing with the 1 kilo. Imagine putting a 1 it's going to be a equals g minus t. And so what's our acceleration? Well, our acceleration is 1.96 is equal to g, which is 9.8, minus t. Hence t is just 9.8 minus 1.96. And pretty much that'll be it. So 9.8 minus 1.96, which is 7.84, which is D as your answer. If you want to double check, say we used mass, the 1 kilogram mass to calculate, we can also use this mass over here and resolve it to get the same result. For example, let's do this question. So of course we're going to write F net, the net force, is equal to the sum of all forces. Well, the only force that's acting in the same direction of the acceleration is that tension force, and that's what's accelerating it. So we're just going to write tension. That's it. And of course, F net is equal to mass times acceleration, which is tension. We know the mass is the 4 kilograms, so we're going to write 4. We know the acceleration is 9.8. Sorry, no, not 9.8. It's 1.96. 1.96. And that should equal to your tension. So 4 times 1.96. And that gives the same result, which is 7.84. Done. Question 9. Let me just rub these out. Not rub these out, but I want to rub these calculations. I don't think I'll need them anymore, these parts here. Which of the following best gives the speed of the 4 kilogram mass when the 1 kilogram mass strikes the ground after falling 4 meters? Let's look at this. Well, we actually don't need these anymore. I don't think so, but... So, if this mass 1 kilograms falls those 4 meters, this also... From here to here will go 4 meters. Imagine this moves down 4 meters. This has to go 4 meters down, 4 meters to the left. So the distance that it will move is 4 meters. Of course, acceleration is going to be the same. And we know, so we can actually use our SUVA formula. We know we started at u equals 0 because, again, we started at rest. We know our distance traveled, which is 4 meters. We know our acceleration, which is 1.96. And all we want to try to find is the velocity. Of the 4 kilogram. Well, the formula that comes to my mind is actually v squared equals u squared plus 2as, which does it have all of them? Yes, it does. So hence v is just the square root of u squared, which in this case is just 0. So it's going to be 2a 1.96 s, which is 4. Put that in your calculator and let's see what that gives us. And that gives me 3.9, pretty much 3.96. Which is actually just approximately 4. The closest to it is 4. 3.96. And that is it. Question 10. A linear accelerator, or a LINIAC, accelerates an electron beam to an energy of 100 mega electrovolts over a distance of about 10 meters. After the first meter of acceleration in the LINIAC, the electrons are traveling at approximately 99.9% of the speed of light. The Lorentz factor for an electron traveling at this speed would be closest to what? So that we should know that the Lorentz factor is only affected by the velocity. So this is the formula. It's also in your formula sheet. We know that the Lorentz factor is just 1 over the square root of 1 minus the velocity squared over c squared, the speed of light squared. That's the formula. So I'm just going to pretty much put everything into that. So Lorentz factor is equal to 1 over, I'm going to write a big one. A nice big one like that. Alright, so I'm going to put a square root. Okay, so it's going to be 1 minus the velocity. Now, because we know it's 9.9, so it's gone 99.9% of the speed of light, that's actually just the same as 0.999, sorry, 9 times the speed of light. 3.0 times 10 to the power of 8. And that's all going to be squared. All divided by c squared, which is the speed of light squared. So 3.0 times 10 to the power of 8 squared. And let's put that in our calculator, and that's going to give us our Lorentz factor. And that gives me 22.36. So looks like A is your answer for that one. Nice. Question 11. An alien spaceship has entered our solar system and is heading directly towards Earth at a speed of 0.6 c, so 0.6, so pretty much 60% of the speed of light, as shown in the diagram below. When it reaches a distance of 3.0 times 10 to the power 11 meters from the Earth in the Earth's frame of reference, the aliens transmit a be there soon signal through a laser beam. You should know always, a laser beam has the speed of light. So anytime you're doing questions in the VCA questions, the speed of a laser is actually the speed of light. So we know the velocity of this laser beam is just 3.0 times 10 to the power of 8, which is the speed of light. How long will it take for the signal to reach Earth according to an observer on Earth? Easy. So we know the distance between the spacecraft when it we know the distance from the Earth to the alien. So the distance is what? 3.0 times 10 to the power of 11. And the speed, which is 3.0 times 10 to the power of 8. Remember, the speed of light, so the speed of light, by Einstein's second postulate, it states that the speed of light is the same for all observers, regardless of the motion or the motion of the source of light. So anytime you're doing question, the speed of light is not changed. It's always the same. That's the key here. So that's why it's just going to be 3.0 times 10 to the power of 8 we use. So we want to calculate that time. How long would it reach the signal to the Earth? So we know that distance is equal to voltage, velocity over time. So hence time is just going to be distance over time. So let's write that. Distance over velocity, which is in this case 3.0 times 10 to the power of 11 all over 3.0 times 10 to the power of 8. Let's put on a calculator. And that gives me 1,000 seconds. Beautiful. 12. A golf club strikes a stationary golf ball of mass 0.04 kilograms. The golf ball club is in contact with the ball for 1 millisecond. The ball moves off at 50 meters per second. The average force exerted by the golf club on the ball is closest to what? So what we have is we have a golf ball. So let's just draw a golf ball. And so it's stationary, so U equals 0. And the mass is 0.040. And so imagine we have a golf club that has hit it. Has hit it. And now the ball is moving with a velocity of 50. And what else do we have? And yes, the time of contact is a millisecond. So T equals 1 times 10 to the negative 3 seconds. Anything else we have? That's it. So if you don't know, we want the average force. You should straight away come to your mind. Impulse is just force times time. We have the time, and we also have the impulse, because we know impulse is just a change in momentum, which is m v minus u, hence equals ft. And so divide both sides by t, we just get the force. So the force is equal to this. Now just imagine subbing everything in now. We just have to sub in everything. So in this case, let me just rub some stuff out. Put some here. Let me put it here. Let's put it. So mass is 0.040. The velocity of the ball, final velocity, is 50 minus your initial, which is 0, all divided by the time in contact, which is 1 times 10 to the power of negative 3. Let's put that down in our calculator. 0.04, 50, 1 times 10 to the negative 3. And that gives me 2,000, which is the same as C. Done. Which of the following statements about polarization of waves is true? First of all, polarization of light only occurs, you should know that, basic knowledge. So polarization of light only occurs for transverse waves. Whenever you hear the word polarization, it only works for transverse waves, not longitudinal. And it's pretty much, what is polarization? It just, polarization restricts the direction of wave oscillations to one plane. The best way to actually explain it is to kind of draw a diagram. And so let me show you. So if you have, for example, let's just draw an arrow here. Say, we have what we call a polarization filter, this filter here. And so it only lets vertical, it's a vertical polarization filter. And say, for example, we have a wave that's propagating vertically. Because it's propagating vertically, it's actually going to pass through this, and it's going to actually pass through it and move on nicely. But what about if we had a transverse wave horizontally, for example, like this? Now, this vertical polarization paper is actually going to block it, and hence nothing is going to be out. It's not going to come out. And that's what it is. So that's the best way to explain it. Yeah. So let's have a look at the options. Only electromagnetic waves can be polarized. Look, I know. So electromagnetic waves are a type of transverse waves, but it's not only electromagnetic waves that can be polarized. Also, mechanical waves can be polarized too. So yeah, not just electromagnetic waves. Be careful with that. They're trying to trick you here, because many students know that electromagnetic waves are transverse waves, but they're only saying only. And you also remember mechanical waves can also be polarized. B, both longitudinal and transverse waves can be polarized. No, only transverse waves can be polarized, not longitudinal. C, longitudinal waves can be polarized. Nope. D, transverse waves can be polarized, but longitudinal waves cannot be polarized. Beautiful. And yeah, again, just let me explain it. Polarization, it's like it restricts the direction of a wave oscillation to one plane. As we can see, this is the one plane. It will only restrict, to the vertical direction. And it doesn't let the horizontal direction pass through it. Let's have a look at 14. Which of the following best describes electromagnetic waves? First let's understand what an electromagnetic wave is. It's pretty much a transverse wave, as we said from the last question, and it's made up of mutually perpendicular oscillating electrical fields and magnetic fields. That's the basics of an electromagnetic wave. Let's have a look at the options. They all travel at the same speed in all mediums. Rubbish. No. This doesn't make sense, because if you have, like, say, electromagnetic wave traveling through air, it's actually great because it's, traveling fast. But if you take the same electromagnetic wave and put a different medium, for example, water, it's going to slow. The speed's actually going to slow. And so that's not right. They don't actually all travel the same speed at all mediums. That's wrong. Let's look at B. They all travel at the same speed in a vacuum. Beautiful. We know that electromagnetic waves in a vacuum travel at the speed of light, and it's constant. So B is the true answer, I would say. I'm just going to put it correct on that first. Let's check the other ones. They are not reflected by a surface. No, electromagnetic waves can be reflected by a surface. They can be reflected by a mirror or reflected by a metal surface. Yeah, they can actually be reflected. So also C is wrong. D, they always travel in a straight line. Not really, because say if you have two mediums, like water, like we said, if you had mediums, say, you pull an electromagnetic wave. Because, say this is water. Say this is water here. It has a higher end value, hence it's slowed down. So it could be like this, or well, it's not like that, but yeah, this is not traveling. If it's at the same mediums, then it will travel at the same straight line. But in this, it wouldn't actually travel in the same in straight lines. Because by refraction, it's gonna be bending. So yeah, B 100% is right. So I would choose B. D is quite confusing, but they always travel in straight. No, they don't. Not always. If there's two mediums, they can actually be refracted, and hence, not moved at an angle. Their angles will be changed. So I'll say D is wrong too. 15. Which of the following best gives the different regions of the electromagnetic spectrum in order from the longest wavelength to the shortest wavelength? Easy. This should be written in your formula sheet. So I'm just going to have a look at my formula sheet. You don't have to memorize these. Just put them in your formula sheet. Here it is. So from the longest, so high wavelength, which is equal to the lowest frequency, all the way going to the lowest wavelength to the highest frequency. Remember, the wavelength and the frequency are inversely proportional, means that if you have a higher frequency, you have a lower wavelength. So we know, going by this, we know it's going to be, the first is radio, microwaves, infrared, visible. Make sure you have this in your formula sheet. It tends to come in the exams. Yeah, ultraviolet, X-ray, and gamma. And that's from going from the pretty much the lowest frequency to the highest frequency, or in other ways, the highest wavelength to the lowest, which in this case, that's what we want for this question. Let's look at A. Ultraviolet visible light. No. Ultraviolet's here and visible light. You're going backwards. Nope. B. Microwaves and ultraviolet. Let's have a look at micro, ultraviolet. Okay, that's good. That's increasing. Visible light. No. Then you're going over here. That's not in the order. See, visible light, yes. Ultraviolet, yes. Infrared, no, infrared's backwards. It has a lower frequency than those. So C's are not right. D. So it says microwaves, beautiful. Infrared, yes. Visible, yes. And ultraviolet. Can you see how they're going all in order? That's your correct answer there. Choose D. Easy. Question 16. When light of a specific frequency strikes a particular metal surface, photoelectrons are emitted, okay? If the light intensity is increased, but the frequency of the light remains the same, which of the following is correct? Now, you should know that if light intensity increases, what happens? The number of photoelectrons increases. Which hence increases photocurrent. And remember, frequency, it doesn't affect the number of electrons. It just affects the kinetic energy of the photoelectrons. In this case, we're not even touching the frequency. We've only increased the intensity. So yeah, let's have a look at the number of electrons emitted. Yep, as we said, will increase. So not B and A, it increases, we said. And the maximum kinetic of the energies will be the same. Remember, the only thing that affects, the maximum kinetic energy is the frequency of the light being used, not the intensity. It doesn't affect it. So, C is your answer. Nice and easy. Question 17. A metal surface has a work function of 2 electrovolts. The minimum energy of an incoming photon required to eject a photoelectron is what? Wait, pretty much that just defines the work function. Remember, the work function is the amount of energy required to free the most loosely bound electrons. And this is what we want. We want the minimum, means the lowest energy of an incoming photon required to eject electrons, which is this over here, the work function. So what we just want is to convert the work function to joules. And how do you do that? You should know that it's just 2.0 multiplying it by 1.6 times 10 to the negative 19. Nice and easy. Times 1.6 times 10 to the negative 19, which is 3.2 times 10 to the negative 19, which is that. Looks like A is your answer. Nice and easy. Question 18. A student measures a very small current in a circuit and obtains a result of this. The number of significant figures in the measurement is what? Now, you should know your significant figures. Remember, the zeros on the left side do not count. It's only the zeros on the right. And yeah. So, for example, here, a lot of students might be like 1, 2, 3, 4, 5, 6, 7. Oh, we have 7. Or like 6. No. We don't count the zeros on the left-hand side. So all these zeros are rubbish. It's only these. So that's 1, 2, and 3. Remember, the zero that I counted on the right is taken 2. Only zeros on the right are to be taken. So in this case, it's going to be this 1, 2, and 3. We have only 3 significant figures in this question. B. Question 19. An independent variable is best described as what? Now, you should know what an independent variable is. An independent variable is a variable that you manipulate, and it hence affects the dependent variable. So think of it as like the x and y axis. When you affect the x, like when you do changes to the x values, it affects the y values, it affects the output. So let's look at this. So it's set by a researcher. Yes, the independent variable is pretty much set by the researcher. That's put a tick. Is not relevant to the experiment. Rubbish. It's very important to the experiment. C, fixed throughout the experiment. That's just a control variable. No, the independent variable is the independent variable. Yeah, here they're talking about the control variable. Be careful. It's not fixed. Not related to any other variable in the experiment. No, it is related to the dependent variable, because whatever you do to the independent variable, it will affect the dependent variable. So A is your answer for that one. And the last question, 20. The main reason for repeating an experiment is to what? So if you should know that when you repeat an experiment, you are actually decreasing the chances of making random error. So like random error means human error. And so you're decreasing that. But be careful. Don't think you're decreasing systematic error. Systematic error means like if you have equipment that is faulty and say, it's off by some value. If you just keep using it, it will always be off in the, by some value, and hence it will be constant. The actual error will be constant throughout the experiment. So systematic error does not, repeating the experiment many times does not have any effect on the systematic error. So the systematic error is actually just constant throughout the experiment. So that's the most basic. Whenever you see a repeating experiment, think of random error being decreased. So let's look at A. Reduce the random error. Beautiful. Reduce systematic error. Wrong. C. Allow for differences between researchers. What? That's not the main reason for repeating experiment. Repeating experiment is to decrease the random error. Absolutely C is wrong. D. Allow for variations in control variables. Rubbish. Yeah. A pretty much is the best description of why we repeat an experiment. We always repeat experiments to reduce human error, which is random error in this case. And yeah, I hope you guys learned something and can check your solutions. Thank you guys for watching, and please make sure you like and subscribe to for more videos. And yeah, have a great day, guys. Bye bye.